Hi everyone. Make sure that you can hear me. I recently lost my voice, so in addition to speaking only in English, I'm sorry you're going to have to do with a little bit of a hoarse American accent at this point. So I'll try to speak as clearly as I can, but if you have any questions, feel free to stop me, interrupt, and raise your hand and we'll circle back. So the topic of my presentation today is on 100 gigabit Ethernet and beyond. Basically, I want to talk about the 100 gigabit Ethernet technologies that are being deployed today, and the routers and the different interconnects and optics that are used to deliver that kind of service. So I'm going to start off talking about a little bit about just an overview. Then we're going to move on to the signaling that's used inside the box. This would be the 28 gigabit common electrical interface. Then a little bit about the signaling that's used outside of the box, the optical signaling. There's a couple options there. And then a little bit about the media modules themselves, the SFPs and CFPs, and different pluggable optics that you can use with 100 gigabit Ethernet. And then last, we're going to talk a little bit about what's been happening recently with 100 gig E and where Ethernet is going from there. So what we're going to see after 100 gig Ethernet is deployed in the next couple of years. So there's a lot of different standards bodies involved in any kind of conversation like this. I just wanted to put their names out there and give you kind of a sense of who does what and what they're responsible for. Working from the top down, it's essentially set up here like the OSI model, so you can get some sense of how the different standards bodies interact. And also of note, as you move up towards the top, that's where operators are actually involved as well. So the current state of 100 gig E is best defined by the IEEE standard that was recently released. 802.3BA was approved in 2010, so it's been a while now. It's pretty well standardized by the IEEE. The first generation of equipment is being deployed in production networks. The test gear is out and it's stable, and it's hit the field. But right now we're in what I would call the first generation of 100 gigabit Ethernet. So in the first generation of 100 gig E, we're using a 10 by 10 electrical interconnect, and then we have two choices of optical interconnect outside of the box. And this is basically the core of the presentation here that I want to talk about, is the difference between first generation 100 gigabit Ethernet and second generation 100 gigabit Ethernet, and even what to expect from the third generation of 100 gigabit Ethernet. To give you some sense, we're already at what I would say is the third generation of 10 gig E. So we're just starting this process with 100 gig E. So the difference between the two all comes down to the signaling that's used. This is, if you look at this block here, it's pretty hard to see on the display, but what we have here is an optical module. This would be the pluggable optical module that is equivalent to the SFP in 10 gig E, the CFP. This pluggable module communicates with the router, the switch, or the equipment using electrical interface. And today, in the first generation of Ethernet, this electrical interface is essentially a parallel connection of 10 gigabit lanes. There's 10 parallel electrical connections that drive 100 gigabits of data towards the optical module. Inside that optical module is then a converter that converts that 10 by 10 electrical signaling into a 4 by 25 electrical signaling. So this is an ASIC. It's just simply a chip that's a serializer, deserializer that converts one parallel interface to another parallel interface, which then drives a number of photo diodes or lasers to signal optically out of the SFP or the optical module. At the top, it works in reverse the same way, or actually at the bottom, it works in reverse the same way, driving the inputs that come in at 4 by 25, turning it into 10 by 10. The reason that this is important is that this is a rather complex ASIC to have on your optical module. This is something we'd rather not have at all, to have to do this electrical conversion inside a pluggable optical module. It's a pretty big sized chip, and it's one of the reasons why the pluggable optic is so expensive and so complicated. And it's what makes it first generation. In the second generation, we move over here, you're going to see that instead of having a 10 by 10 interconnect, you actually have a 4 by 25 external electrical interface to the optical module. So the optical module is going to communicate with the system at 4 by 25, which is the same speed that it communicates optically with the box that's on the other end of the link. So there's no electrical to electrical conversion. It goes in 4x25, it goes out 4x25. That leads to a much more cost-effective optical module. It allows us to make the router simpler. That's what's going to drive 100 gigabit Ethernet density into the second generation. So a little bit about that common electrical interface, just so it's clear what we're talking about here. There's a number of different initiatives that are being done to actually develop this 25 gigabit electrical interface. First, the first one would be the SerDes development that actually takes place on the backbone of routers and switches. This is the interface that line cards use to talk to each other. Right now, that's not 25 gigabit yet. Then there's the line card internally on itself, chip-to-chip interfaces, and actually the one that's most important to us, the chip-to optical module interface, number 2 there. So where that stands is that it's just finally getting stabilized at 28 gigabit per second electrical interconnects, and it's just like within the last month reaching standardization. So the OIF is responsible for this, and they've basically defined this 28 gigabit per second electrical interface that we need, which means that obviously since that's just been standardized, that's why none of the equipment that's deployed today, the Generation 1 equipment, uses this interface yet. But what it does allow you to do is create, it supports 32 gigabit fiber channel. It can do 100 gig using 4 lanes, or it can do 400 gig in the future using 16 lanes. And as I said, it's recently completed as of a couple months ago. This is Generation 2. All right, so a little bit about Generation 1 and what we see on the outside of the optical module. So this is what's going on, not between the pluggable optic and the router, but actually between the pluggable optic and, let's say, the fiber or the other pluggable optic on the other side. So this is how the optical signaling itself is done. There were basically 2 approaches to this. The IEEE came up with their standard, the 100 G base LR4 and SR10, and you know, they're the IEEE. This is their responsibility. They do Ethernet, and this is what they came up with. The problem was it had a couple of gaps. This is kind of controversial because it upset a lot of people in the IEEE. There's a lot of standards bodies getting mad at each other. A lot of people left off each other's Christmas card lists. But essentially, the IEEE had a couple of gaps in the very short reach and the very long reach. The very long reach was a little too expensive, and the very short reach used multi-mode high-density cables instead of single mode. So a number of different operators, vendors, and different parties got together and said, we really need a different approach for this. And you can see the members that got together here formed the 10x10 MSA Alliance. So rather than use the 4x25 optical signaling that the IEEE defined, the 10x10 Alliance said, no, let's also use a 10x10 optical signaling. So in addition to, so as I had shown before in the electrical signaling, where you have 10x10 electrical signaling between the router and the pluggable optic, the 10x10 Alliance says, let's use that same electrical signaling to do a first generation optical interface as well. So the downside here is that the good news is that you have more choice. So both of these modules in a sense are interoperable, because it doesn't matter if you have a IEEE 100G base module or a 10x10 MSA module. They're both going to plug into the same slot. They're both the same modules. They both use the same electrical interface. The difference, as you can see in this picture, is that at the top here, the IEEE model, it requires that chip to be built into the SFP, as I had said, because it requires that if you interface at 10x10 and optically you're going out at 4x25, you have to have some kind of silicon, some kind of ASIC inside the pluggable optic that's going to do that conversion, that electrical to electrical conversion. The 10x10 alternative, the 10x10 MSA, on the other hand, uses that same interface. So if you look, as far as the router is concerned, it's driving it the same way with 10x10 electrical interface. The difference is there's no chip. So there's no electrical to electrical conversion. And this, the 10x10 signaling then drives the lasers directly, and it, instead of driving 4 at 25 gigabits per second, it drives 10 at 10 gigabits per second. So interestingly though, this does create a little bit of an optical challenge for the 10x10 group. So up at the top, you only have to multiplex 4 optical signals together onto a single fiber. On the bottom here, you have to multiplex 10. Optically, that's a little more difficult. There's certain optical issues there with dispersion, with crosstalk, with noise, and with loss that you have to deal with. But they're much easier to overcome than putting an extra piece of silicon in each module. So at the end of the day, the 10 by 10 Alliance, which Brocade is a member of, fair disclosure, but then again, so are most of our competitors, really delivers an alternative to the IEEE approach that allows you to buy lower cost optics that plug into the same modules that deliver 100 gigabit Ethernet for a lower cost. In the future, and this is all generation 1, right? In the future, this electrical interface that's 10 by 10, which makes this cheaper, goes away. So this is what the IEEE was saying, was that the reason the IEEE didn't do this was they were saying, look, we want to get away from 10 by 10 as quick as possible. We want to go to 4 by 25 because that's the next generation. They didn't want to do this standard essentially because it kind of blurs the line. It makes it puts less rush on getting to the 4 by 25 model. A lot of this is my opinion, but I think that's a fair bet. So the 4 by 25 model uses this is the second generation of electrical signaling inside the box. Once we get to this, the 28 gigabit common electrical interface, once we get here, the need for this goes away. You don't need this gearbox anymore because the electrical signaling is already at 4 by 25. So without that additional need for that conversion, there's really no need for this. And we kind of move to what is called second generation gigabit Ethernet. So you get all the benefits and none of the disadvantages of this approach in the second generation IEEE approach. And that's where we'll be going, now that it's standardized, that's where we'll be going in the next couple of years. Okay, so what do these modules look like? Before I get to the 100 gigabit stuff, let me just turn the clock back. And this is really important because everyone in the industry expects that the development of 100 gig will follow the same basic track that we saw with 10 gigabit Ethernet. So I'm sure all of you remember this evolution where we started with something that wasn't actually pluggable in the first generation of 10 gigabit Ethernet. It was huge. This is a relative size. And now we're all the way down here, 7 years later with SFP pluses that are tiny, and you can fit 48 of them on a single line card. So, in the 7 years that we went from non-pluggable first generation all the way to third generation, tiny little, almost too hard to handle pluggable optics, we're expecting the same thing will happen in the next 6 years with 100 gigabit Ethernet. And you can see we had the same question of electrical signaling going on. The first generation of 10 gigabit modules used a 16 by 644 megabit signaling. So they use 16 lanes running at about an OC12 or STM4 rate there. And then we've moved all the way down till we finally get to the point where we can actually do it serially with just a single lane of 10 gigabit per second in the XFP and the SFP plus. And that's what really makes those tiny little SFPs and XFP pluses possible, is the fact that you don't need to do any electrical signaling. It also makes it possible to do the DWDM SFPs to fit all the silicon that you need to do actual OTN encoding and things like that you can do on an XFP these days. But this is where we are today. So today, in the current generation, the first generation of 100 gigabit Ethernet, this is essentially what the module looks like. The good news is that we started off pluggable. So unlike the first generation of 10 gig E, where you actually had the module soldered to the board, and if you wanted to change out a short reach for a long reach, you had to replace the whole line card. At least you don't have to do that with 100 gigabit Ethernet. We learned from that mistake. But the pluggable module itself is huge. It's the size of it's bigger than an iPhone. So it's quite a bit different from an SFP plus. It does run 10 times faster, but it's pretty different. And so the downside is you can only really fit 2 of these on a board. So right now, there's pretty much a limit to about 2 per 1U pizza box. Where are they going to go? So this is, obviously this is predicting the future, so your mileage may vary. But the first generation and second generation, my voice is going to fail me. The first generation and second generation modules are probably pretty certain. The third generation is still up for debate, but as far as the first and second generation goes, I think you can bet that these dates are about accurate. So this is where we are today in 2010. They were released. We'll be going to a 4 by 25 shortly, and you can see how much the module size decreases from this, where we are today, this is a whole different story. I won't talk about that. But how much smaller, you basically get the same functionality you had here in all of these modules just by removing that chip. So by removing that 10 by 10 to 4 by 25 conversion, you get a huge shrink in size. And with that shrink in size comes a shrink in cost, a shrink in heat, and a shrink in power. Again, another way to look at the different sizes of the modules. You can see that little one that I said, I referred to, I kind of glossed over it and said it's a whole different story. It's the multi-mode version of it. It requires a high density multi-mode cable, so it's a very, very short reach. It's not seeing a whole lot of adoption. Doesn't work, it doesn't offer the same kind of flexibility and features that you get with the larger CFP module, so it's not really a fair comparison. Again, you can kind of see them shrinking over time in this picture. I guess there's only so many different ways you can show these modules getting smaller and smaller in time. Okay, so 100 gigabit Ethernet developments. This is what's kind of been like, I would say, the most recent news in 100 gigabit Ethernet. The 10 by 10 MSA group has finished their projects. They are up to about 26 members now that include everyone from obviously vendors like Brocade to customers such as Facebook and Google. And they've completed both the 2 kilometer, 10 kilometer, and 40 kilometer standards. The second generation projects for 4 by 25 signaling have started. So this, what that means is, by started, that means that Brocade and our competitors have started working on this in our labs and our R&D facilities. Nobody has any kind of production 4 by 25 equipment yet. And finally, the IEEE is working on copper interface and backplane interface standards as well. The next would be the IEEE is working on other 100 gigabit optical Ethernet standards, and the QSFP28 and the SFP2 are going to be competing for density in the next couple years. And you saw those were the 2 interfaces at the end, the 2 smallest module size. Obviously, these are just remember, MSAs aren't quite as formal as standards bodies, so they tend to form small groups and fight it out, basically between the module makers. So there's still going to be that SFP plus versus XFP debate, and which is better and what offers more. So expect that to continue in 100 gig. This is what it would all look like as far as first generation and second generation. A little bit about what you can do with the CFPs today, and all the different options that you're going to have with the second generation signaling. I'm not going to go through this slide. I just put this in here for the sake of reference. If anyone needs it, it's going to be handy. I think in the time to come, you can pull up the presentation from the website and be able to see all the different standards, all the different reaches and modules that are going to be available in the next couple of years. So beyond, I did promise some beyond 100 gigabit Ethernet. So this is kind of our, how many times have you seen this graph, right? The usage just keeps on going up. It keeps going, people want more and more and more as time goes on. But the thing that's really important about this graph is that it's very predictable. These dates are very accurate as far as when we've needed stuff, and it's very predictable, very linear. So it looks like by 2015, we're really going to need something a lot faster than 100 gigabit Ethernet. And what that means is that we're going to have to start planning soon. So what do we do to go past second generation and past 100 gigabit Ethernet? It's going to be a trade-off. There's always going to be economics. We're going to need input from customers. We're going to need input from manufacturers to understand the different options that we have to go after that. And you can bet that it's going to be a trade-off. It's going to be either big or fast or cheap. It's going to be 2 of those, but you're probably not going to get all 3. The important thing is how long it takes to get through the standards body. In my opinion, this is the most important aspect of that growth curve. Is that if you look at how long it took 100 gigabit Ethernet, we started that in December of 2005. We finished in June 2010. And as I said, we're going to need by 2016 something faster than 100 gigabit Ethernet in the terabit Ethernet speed range. So if that's the case, we need to start that planning now. So the IEEE has already started this. I think that's on my next slide. They've already started a bandwidth assessment ad hoc committee. They're gathering input. They are collecting it from anywhere they can find it. So, you are some of the most important users of this high-speed gigabit Ethernet technology. If you have any input, like you're sick of yellow and orange cables and you think we should go to pastels, let them know. These are the, hopefully your input's a little better than that, or at least don't tell them I told you how to get in touch with them. But, feel free to send that input, what you need, what you're seeing as problems. Now is the time, because these processes take so long to develop that we really need to start that process as soon as possible. All right, so future 100 gigabit Ethernet projects, the short term, that 4x25 change going from 10x10 to 4x25 electrical signaling, that's going to take a couple of years. So that's how long it took with 10 gigabit Ethernet to go from that first generation to the second generation. It's going to take a similar amount of time for 100 gigabit Ethernet. So we're really looking at about 2 years before we move to that faster electrical standard. 100 gigabit Ethernet serial, that would be 1x100. So we're going 10x10, 4x25, then 1x100. The serial option, that's really the ultimate, right? I mean, you can't get faster, can't go less than 1. So, that's the ultimate solution. That's going to be a real challenge. It took a long time to do 25. Nobody really even has that on the roadmap as far as the standards bodies go. So that's going to take a long time. And I think that until we have that, we really don't have a solution for terabit Ethernet. So terabit Ethernet will probably come out when it comes out, and this is considerably in the future, using a 10x100 gigabit signaling, because anything else is just too massive. Third generation 100 gigabit Ethernet is probably going to be, like I said, several years from now. So what are we going to do? If we're not going to go right from 100 gigabit Ethernet to terabit Ethernet, what are our options? Well, we could go to 250 gig Ethernet. We could take our 10 model and go 10x25. We have 10x10, so and we'll have 25 gigabit lanes, so we could do 10x25. That would be very doable. Manufacturers would, be very content to build that. It would be a very low bar for us. I'm sure we could spit that out rather quickly. The problem is nobody wants it. Nobody really wants a 25 gigabit Ethernet, so that's off the table. 300 gigabit Ethernet would also be an option. You could use 12x25. That's nice. It sounds kind of silly, but it's nice because it matches the number of fibers in a multi-mode, a dense multi-mode fiber bundle. So it actually fits quite well, but just like 250 gigabit, it's just not fast enough. So the most likely candidate for the next stop is 400 gigabit Ethernet. In a sense, 10 times 40 gig E. It'll use 16x25 gigabits for electrical signaling, and 16x25 gigabit, or 16 25 gigabit wavelengths as well. Optically, that's actually almost as much of a problem as it is electrically. So getting that to go a distance without causing problems is a challenge. That's what, that's better than most DWDM systems use today, and we're going to put that all in a little SFP. So terabit Ethernet in the future, obviously 40x25, it would be a gigantic module. It would be, DVD sized at least. So you'd only be able to get one of them on a standard pizza box size line card. So like I said, I think that's going to have to wait until we figure out how to do 100 gigabit electrical interconnects. So what does the 40 gigabit Ethernet module look like? Very simply, it's probably got 16x25 gigabits electrical signaling. It probably, having the IEEE, having learned from the past, the whole 10x10 MSA debacle, probably just directly drives the lasers like the 10x10 MSA module does. And again, this is all speculation, but most likely it'll have 16x25 gigabit wavelengths running on a single twisted fiber, and it should be able to reach at least 40 kilometers. Okay, so in summary, first generation of 100 gig E today uses 10x10 electrical signaling, and you have two options for optical signaling. You can either have 4x25 using the IEEE approach, or you can have 10x10 using the 1010 MSA approach. Both of those modules will work similarly in different systems from a manufacturing standpoint. it's just as easy for me to support either optics module. It doesn't take any more work. They both have similar electrical and thermal requirements and things like that. The second generation will be 4x25, so that's when basically everything goes to that next generation. You have 4x25 electrical interfaces, 4x25 optical interfaces, no mixing and matching electrically inside the module. The industry is probably going to be working on this for the next 2 years though, so that second generation is still quite a ways in the future. And then probably after that, you're looking at 400 gigabit Ethernet. This is in the 2013 plus for a standard, but we're really talking about like 2016 for a 400 gigabit Ethernet standard. And then of course, terabit Ethernet is fun to talk about. If for no other reason, then we get a new acronym. That's quite a ways off though, so it'll be some time. That's all I've got. Are there any questions? Yeah, that's a good question. I know exactly what you're talking about because it's always confusing when you talk about this stuff, who you talk to. So I'm a router vendor, right? And if I was a DWDM vendor, I would have had a whole lot of slides in here about modulations, and it's exactly what you're talking about. On the DWDM side, I left out this whole complex question. It's a transmission side thing. And the transmission guys, they have a different problem, right? Like, as I said, I've got 4 lambdas on one fiber, and I say that's good, right? Because I don't have to share that. I assume I don't have to share that fiber with anybody. But to a transmission guy in the DWDM world, I can't use 4 lambdas for one router. For one thing, they all overlap, so I can only have one router on that fiber. The DWDM guys have to get to 100 gigabit serial, right away. That's like their first generation. It has to go there right away. And they have the luxury though of building giant modules that don't have to have packet lookups and things like that. All the stuff that goes behind the module is much simpler for them. Mm-hmm. Yep, and doing it in a dense way. So making sure that you can, anything's possible. Like I said, it's much easier for the transport guys, for the DWDM vendors. Yeah.
It will be like a modulation or something like that.
Yep.
So it's not going to be any problem anymore.
And that's absolutely true because today in 10 gigabit Ethernet, you can get DWDM qualified pluggable modules so that they come out a very specific frequency, right? And in the third generation, when we get to the third generation of 100 gig E, that's when we'll be able to do the same thing that we can do with DWDM today. But again, that's like 2016, so I'd love to talk about that, but that'll take some time. And it is interesting. This is actually a bigger problem than I even indicated here because on the DWDM side, there's no interoperability. So there's actually like 16 different ways you can modulate that 100 gigabit Ethernet carrier, and nobody agrees on like which one to use.
Okay, so. But could you please maybe you know how much are the needs for the like a level 3 or somebody else like such a huge operators?
Yeah.
How much they need at the moment? So
they definitely use it.
Okay, you have 100 gigs, but it's not enough for us.
I can't without speaking. You mean like you're asking like who uses 100 gig E and like how much is it used? I'm obviously not going to be able to say, well, operator XYZ uses this much, but I will say that some of our larger operator customers currently have link aggregation bundles that are 10 gigabit Ethernet that are already over 100 gigabits. So they have 16 and 32, 10 gigabit Ethernet lags, and they'd be thrilled. They're so happy to get 100 gig. So there is a
possibility to do it like 16 times or 32 times because currently the devices that I've met they have a limitation up to 8. Well,
this is just lag. So then you need 16 fibers, right? So this is like 16 actual 10 gigabit connections. Yeah, without talking too much about Brocade, yeah, we can do higher bundles of lags. But that's good, and it's great that we can do that. Everyone can do different levels, but eventually you want to move to the next higher standard, so you don't have to manage 16 links, right? And that's why 100 gigabit Ethernet is getting pushed so hard.
For next 2-3 years, let's say 3, 4, 600 gigs per router would should be enough.
Yeah, I think so. And you know, we're doing, you know, this is NOG, so I like to be fair. You know, Cisco, Juniper, Brocade, we're all doing 2 gigabit. I could argue about who's doing it better, but I'll say that the density of 2 ports of 100 gigabit Ethernet is a pretty easy to find commodity right now. So you can get 2 ports of 100 gig from different vendors. And that seems to be enough. There isn't a whole lot of push to go too far beyond that right now, but I think next year we'll start seeing it. We do see more in like data centers. So where you get like very large data centers and cloud deployments and things like that, then they start to run out of slots. But there's never enough bandwidth for them. So you can just always, if I had a 4-port, it wouldn't be enough.
Okay, so should the internet be worried about lack of capacity?
No.
You
I
don't
mean,
think so?
no. Lack of capacity is. I think you know, when you look at the history of 10 gigabit Ethernet and how the backbones have grown like linearly and how we've kept pace, I don't see any reason why we're going to stop.
So all the time the technology could be faster than the needs.
At some point, it's going to. I actually think at some point the need will start to taper off just a little bit.
Okay, how much can you download?
Yeah, exactly. How much video can you watch? When you can watch the entire all the video ever recorded in the history of the world in like 5 minutes, like, you know, that's enough.
Okay, thanks.
Yeah. All right. Nobody else? Thank you, everybody. I appreciate it.